Welcome to lecture 22. In this lecture, what we want to do is provide examples on how you can construct functionals from governing equations. It will become apparent when I cover approximation theory on why this could be useful. But for now, what I want to point out is that I will go through some examples on how to construct functionals. And functionals, uh, remind you a little bit about functionals. Functionals are functions that depend on other functions. And what we're looking for is the function that extremizes the functional. And so with that said, let me go through the first example. And the first example, I want to give a heat transfer problem. Example number one, consider the example of a heat transfer problem, which is given by this, in case the conductivity of the material, and I'll further write it in this manner so it's clear what the example really is. And then you have the convection coefficient T. T is the temperature, Tf is the temperature of the fluid, and this is equal to 0. And I'll specify the temperature at both boundaries. So in this example, we're assuming that x goes between 0 and L, and that the temperature at x equals 0 is T naught, and the temperature at x equals L is TL. So what I want to do now, I'll try to write this in a simpler format. So I'll write it as this being the governing equation, AKT prime prime minus HT minus TF equals 0 to make it easier. And so the next step is to form something called a weak form. So I'll multiply everything by del t. I could multiply by a test function v, but I'll multiply by del t because it's more obvious what I'm trying to do and what the boundary conditions are telling us. When I do that, I'll go ahead and write it so you can see it. Like that. So I'll integrate this over the domain. And now that becomes like this. And I write each term separately for convenience. And now what I'm going to do, my goal to create a quadratic functional, again, what I'm trying to do is come up with a functional that describes this governing equation. What I want to do is bring this prime. I want to basically put a number of primes the same on this variable compared to this variable. Clearly, the variable of interest is t because I'm trying to solve for the temperature T. So my first step then is to go ahead and integrate by parts. So I'll do that now, del t. And again, my goal is to see if I can bring equal number of derivatives to the left and the right. So I have a prime there now, and I have a single prime on the right. So that should be enough, plus, minus. And so now I can write this as 0 to L. Like that. Nothing else needs to be done here. And now I have the boundary conditions, plus, and this is occurring at x equals L. And this is occurring at x equals 0. Now note that the temperature specified both boundaries. So del T has to be 0 at this boundary, and del T has to be 0 at that boundary. So then, if I want to construct a quadratic functional, all I have to do is examine this term, and that term. And you can see here that for me to be able to get what I have there, I must have a functional that looks like this. I t of x equals 0 to L And clearly I have a minus 1 half ak t prime, and this right here should be squared, and that's the only way for me to go from here to here. If I want to find the first variation of this, I'll get that term there. For me to be able to get that second term, I have to have minus 1 half h t, and I'll make del t squared, that's approach, and add a 1 half, and I have plus, and I definitely have a h times tf times t for me to be able to come up with a functional dx. And you can see here when I find the first version of I, it will result automatically in what I have here in this expression. So that's a functional for this particular problem. Clearly, I have a functional. If I have a functional and I were to render this stationary, this functional stationary, you will find that it will be a minimum when you solve this governing equation here that's given to you. So that's example number one. If you're still in doubt that this actually works out, call this f for a second. For a second, so you can see. So f is minus 1 half ak t prime squared. So the first variation of f is the derivative of f respect to t prime del t prime. Well, that is equal to minus 1 half ak times 2 t prime, and now I have del t prime. 2 and 2 cancel out, so I get minus ak t prime del t prime. You can see clearly that this is exactly what I have here. I can do the second term as well, so you can see it. Let me call this g and this h, so you can see everything works out very nicely. So g is 1 half, and in our example we have ht squared. So del g is partial of g respect to t del t, and clearly that's minus 1 half h times 2 t del t. 2 cancels out, I get minus ht del t, and you can see that matches that second term there. Let's look at the third term, which I called h. That term h, if you look at it in the functional, I called it htf t. So therefore, the variation of h, it only depends on t, so it will just look like that. And there I get only htf del t, which is exactly, I apologize for that. You can see here that I get that term right here. I got that term, I got this term, and this term, as you saw in the next page. So that's a functional for this problem. Let's look at another example. I think it helps to look at different examples. You can see how functionals are constructed very quickly. So let's look at this differential equation, y double prime plus y minus 8 equals 0. And then y of 5 equals 1. This example is in my book as well, but I modified the procedure so you can see how to get there. So that's a differential equation. My goal is to come up with a functional, so I'll take the integral from 5 to 7 and multiply this by del y. And I think I'll just transfer everything like that very nicely. And now the only term that has double derivatives is this one, and I want to transfer half of the derivatives to this one. That's my goal, so I can then get a quadratic functional. So first step, del y double prime, del y prime plus minus. I'm going in reverse, so that's why everything looks weird now. So 5 to 7 minus y prime del y prime plus y del y minus 8 del y dx, and then I have the boundary terms plus y prime del y at x equals 7 minus y prime del y at x equals 5. And this is equal to 0. So what you want to do is look at the boundary conditions. Since y at 5 is 1, del y is specified, so del y has to be 0, so this goes away. Y prime at 7 is minus 2, so you're going to write that minus 2. And so now your functional then, I, which depends on it and on y, is going to be equal to 5 to 7, 1 half, again, here, that 1 half. Anywhere you see del y prime, make it y. So anywhere you see del y, make it y. So I'm going to make that y prime. So I get y prime squared, and I do need the 1 half so that the first variation of that, the 1 half cancels out. So I get exactly what I had at the top, plus 1 half y squared minus it, because if I make this y also, then I get that term. And then if I make this y also, I get that. And then finally I get, again, make this y also, so you get this. And so that is what you will get for the functional. Um, it's customary to write this, the first term as positive. So you could even write this if you wanted to. Everything positive. And now you can take the first variation of I and set it equal to 0. And if you do that, you should be able to find that this is the Euler-Lagrange equations and the boundary conditions. So that's example 2. I think it's a great example on how to deal with that. Let's consider now the example of a bar on the loading conditions and a spring. So example 3. I'll keep doing some examples so we can learn together how to deal with these problems. So EA U prime prime minus KU plus F is 0. So that's the governing equation. And that governing equation is valid between 0 and L. And I'm going to specify boundary conditions. And the boundary conditions are that U at 0 at deflection specified of a value of 0.05. And I have then also a boundary condition that says that EAU prime at L is minus P. And so now I'll again form the weak form. So I'll take the governing equation. And I haven't discovered what weak form is, so just think of I'm multiplying this governing equation by a test function. In the previous lecture, I used V or Z as an example, but I'm doing it differently here so you can see the different ways that people approach the problem. You could have done del U or Z, it doesn't matter, whatever you prefer. But I'm using del U because it's more clear what the boundary conditions are and what is essential versus not. You can see here the only thing that has prime is this one. I will write this actually a little more compact. And the only thing that has prime is this one. That's the one I'll integrate, and I'll try to get the same number of derivatives on either side. And now I'm ready to write that here. Plus the boundary conditions, plus Here is very simple. U at 0 is 0.05, so del U specified, that goes away. EAU prime at this boundary is minus P. And now the only thing to do is now take del U, convert it to U. And if you have U prime on the left and the right, that will be a 1/2. So now my functional becomes this. Sorry about that, 1/2. Like that. And now if you were to find the first version of I and set it equal to 0, the ordered Lagrange equations you should be able to get are the ones here. You should get that. Now, I think I forgot a minus sign. There should be a minus sign here and a minus sign here. So that'll be your functional. I apologize for that minus mistake, but everything else should be okay in this example problem. So I hope it's clear how we did that. Let me tackle a little more complicated example. That looks complicated, but it's not. And it should be okay. So say I have this problem. Differential equation. Looks more complicated, but it's not a big deal. And I'll explain, it's going to become apparent why this is useful to do this. It can be very useful. And, I can call this a number, but I'm calling it M naught. You could call it 5, 10, whatever. But in this example, it's given in terms of variables. This example is also in my book. I think it's useful to look at it. So the first step then is to form the weak form or multiply this by a test function, which I will do now. I'll do it all in one shot and integrate from 0 to 1. Sorry, this goes from 1 to 2. I apologize in this example. And you can see I have no derivatives here. I do have derivatives here, so I want to transfer 2 of them to this side. So then I can have a w double prime squared. So I have to integrate parts at least twice to get there. And so now I have this like that. And I'll write all the boundary terms one by one, which will be a lot of them. Plus this is at 2. This is at 1. And this is at 2. I apologize. The boundary goes from 1 to 2. And this is equal to 0. And now let's examine this carefully. So W at 1 is 1. And so that means that this del W is 0 because W1 is specified. W prime at 1 is 1, so this is also 0 because W prime is specified at that boundary. And then here, clearly, this right here is provided to us in this boundary condition, so that's M naught. And this provided to us in the boundary condition, so that's V naught. So then this one is easy. So that will become, the functional becomes like this. One half, 1 plus x, W prime squared, right? Minus QW. Where I see del W, I'm making it W now. And adding a 1 half on anything that has W here and on the right hand side on the del W. So that's how you're doing it, and plus V naught del W at x equals 2. And again, that's going to be W now. So you just, anytime you see del W, make a W. And so that's the functional for this problem. And notice how there's a prime here. So I'm missing that. But that's the functional for this problem. Very straightforward process to develop the functional. Let me cover one more, and this will surprise you. This is going to be surprising. And I want to come up with the functional for this. So let's multiply by u del w, or del u, I'm sorry. And in this example, I'll expand it. And let's look at this term. Let's look at this term. So I can integrate that one by parts. But here, I'm not able to have the same number of derivatives on either side. I can't have the same number of derivatives on either side. So I'm not sure how to construct a functional out of that, in fact. I don't think there's an easy way to do that. And so if you use the test that I demonstrated for you, whether you have an adjoint or not, a self-adjoint or not, you'll find the self-adjoint test for this problem will fail. You won't be able to get a functional does not cannot be constructed that's quadratic. It's unlikely that this system is conservative. And so I invite you to see if you can come up with a functional. And if you do, please send me an email. And if not, send me the self-adjoint test. Show me that it will fail that test, and there'll be a nice surprise for you. So I hope this lecture shows you a procedure that we're looking for to with coming up with a way of constructing functionals, and functionals constructing functionals is very beneficial. Is beneficial in the discussion of approximation theory. I'll make a few more points when I cover it. If a system has a quadratic functional, the resulting, well, basically it's going to be most likely a conservative process, a conservative system. In this example, you may find that this is not a conservative system if you went through it. And so with that said, I think this concludes the 5 examples I want to give you to continue to build that confidence that you may have. Notice that in this class, what we're trying to do is to figure out ways of approximating the solution to these equations. And so we're just trying to come up with a theory behind all that to build that foundation. Have a good day.